Okay, let's do some examples. That's the easiest way, I think, to see this stuff in action. So here I've got a matrix minus 2, 2, 1, minus 3. Okay, I find the determinant of that matrix and I subtract r on the main diagonal. And we see we get r squared plus 5r plus 4, which I can factor to be r plus 4 times r plus 1. So the eigenvalues are minus 1 and minus 4. Okay. Sometimes I've seen people have problems where they make a mistake with the characteristic polynomial, and then that will just screw up the rest of your problem, which is a big thing, right? Because that's the start of the problem. So there's a couple of double checks that you can do to make sure you've gotten the right answer. Firstly, the product of the roots is always going to be the constant term of the characteristic polynomial, and the sum of the roots is negative the n minus first term, or if it's a quadratic, in the 2 by 2 case, it's the linear term. Okay, so I'd like you to prove that for the 2 by 2 case. That should just be a 2-line proof. So in this case here, minus 1, minus 4, we multiply them, we get 4, that's the constant term. We add them, minus 1, minus 4 gets minus 5. Negative, that is 5. 5 is the linear term of that quadratic equation. The other thing which is super useful is that if you add up the roots minus 1 and minus 4, you get minus 5. You look at the matrix, that's the same as the trace. Okay, the trace is minus 2 plus minus 3 is minus 5. That's always going to be the case. So that's an easy way to make sure you at least start off correctly. Okay, so to find eigenvectors then, firstly you find the eigenvalues, and then you solve the equation a minus ri times u equals 0 for u. Now note, you're going to have at least one degree of freedom, because if you've got an r eigenvector, then any scalar multiple of that vector is also going to be an eigenvector. And question 2 is just prove that. Again, that should just be one 2-line proof. Okay, so let's go back to our example. Minus 1 was an eigenvalue, so we subtract minus 1 from the main diagonal of our matrix. And so straight away you can see that that indeed has determinant 0, because one row is negative of the other row. Okay, so we do that matrix multiplication, we get minus u1 plus 2u2 equals 0. And the other one is, of course, going to be just a multiple of the other one, of the first one. So minus u1 plus 2u2 equals 0, so u1 equals 2u2. Okay, so from that you've got to choose a representative value. There's lots of different ways to do that. The simplest way is maybe just to plug in u1 equals 1 and then solve for u2, or to plug in u2 equals 1 and solve for u1. Others like to have a unit length eigenvector. Just choose whatever the easiest. So looking at the equation, I say, well, let u2 equal 1. And so that means u1 equals 2. So that means you get 2, 1. The minus 4 eigenvector, you subtract minus 4 from the main diagonal. And again, you see that the rows and the columns are dependent. Okay, so the equation we'll use is u1 plus u2 equals 0. So that means u1 equals minus u2. And so if I just let u1 be 1, then u2 is minus 1. So 1 minus 1. Other people would say minus 1, 1. Okay, good. So let's go back to our example. let's look at the ODE system, for example, So converting that matrix then into a ODE system, we get x prime equals minus 2x plus 2y, and y prime equals x minus 3y. Okay, and so for the -1 eigen value, remember 2, 1 was the eigenvector. So let's verify that x equals 2e to the minus t and y equals e to the minus t is a solution to the system. Okay, the way we do that is just plug it in and check that there's true statements. X prime is minus 2e to the minus t, right? Down comes the -1. Whereas minus 2x plus 2y is also minus 2e to the minus t. So check that first equation is satisfied. We take the derivative of y, we get minus e to the minus t, and that's the same thing if we look at x minus 3y. Okay, so for the -4 eigenvalue, we saw that 1 minus 1 was the eigenvector. So your third question is verify that x equals e to the minus 4t and y equals minus e to the minus 4t is a solution to the system. Okay, let's have a look at complex roots. It's really no different from having real roots. The only thing is, of course, that eventually you want to have actually real solutions, but we'll do that later. So here's a matrix 1, 3, minus 3, 1. Okay, we look at the characteristic polynomial of that matrix, and it's r squared minus 2r plus 10. Okay, and we can see it's the right, well, one check for that, right, is that the linear term is minus 2 and the trace of the matrix is 2. So we're doing good. So with that quadratic equation, we use minus b plus or minus square root of b squared minus 4ac over 2a. And we get that is our roots. And so we see that they're complex conjugate roots, 1 plus 3i and 1 minus 3i. Okay, let's find the eigenvectors. So 1 plus 3i eigenvector. We subtract 1 plus 3i from the main diagonal. And again, we get, we see, you should be able to see that the two rows are multiples of each other, right? So you just, if you multiply the first row by by minus I, then you'll get the second row. So I'm just going to use the first row there to get my condition, which is minus 3iu1 plus 3u2 equals 0. So that means I times u1 equals u2. And so if I let u1 be 1, then u2 is I. And so that gives me that eigen vector there. Whereas if I'd chosen u2 to be 1, then u1 is 1 divided by I, which of course is just minus I. And for the other eigenvector, we subtract 1 minus 3i from the main diagonal. And you see that second row now is I times the first row. We get the condition 3iu1 plus 3u2 equals 0, which simplifies to iu1 equals minus u2. And so I let u1 be 1, and so that means u2 is minus I. Whereas if I had chosen u2 to be 1, u1 would be minus 1 divided by I, which is just I. There are my eigenvectors. Okay,